Welcome to a wonderful world where water scarcity meets innovation, where the boundless power of technology transforms the impossible into the possible, where the salt water of our oceans turns into a life-sustaining resource. Imagine a glistening substance, radiant and clear, reflecting the sunlight with an enchanting sparkle. It moves gracefully, shimmering as the sun dances upon its surface. In its freshwater form, water possesses a captivating beauty that cannot be denied. Its purity and clarity make it an invaluable resource for all life on Earth. As Panenta Crystal eloquently expressed, water comes in many forms, from the gentle drip drop of rain to the tranquil ponds, lakes, and flowing rivers. It sustains us as a drinking water and even holds the power to express our deepest emotions through tears. But what about the vast oceans that blanket our planet? Water everywhere and not a drop to drink, a metaphorical representation of the challenges faced by communities with limited access to fresh water. Being surrounded by water but unable to quench one's thirst due to its salinity is ironic. Our oceans hold the secrets to a potential solution to our water scarcity challenges. This is where the wonders of desalination come into play. Desalination holds the key to transforming the vast expanse of salt water into life-sustaining fresh water. It harnesses the power of science and innovation to remove salts and impurities, leaving behind a clear, drinkable resource. By unlocking the potential of the oceans, desalination plants provide us with a pathway to secure water supplies for communities facing scarcity, paving the way for a more sustainable future. While desalination offers a promising solution to water scarcity, it's essential to acknowledge the challenges associated with this remarkable process. The transformation of salt water into fresh water requires advanced technology, a large amount of energy, and resources, making it a complex and often expensive endeavor. The high energy demands of desalination processes constrain power grids and contribute to environmental concerns. Additionally, the infrastructure required for large scale desalination plants involves substantial investments in capital and maintenance costs. Knowing this, let's explore a few of these desalination methods, starting with reverse osmosis. Reverse osmosis is a widely used desalination process that involves applying high pressure to salt water, forcing it through a semi permeable membrane. This membrane selectively allows water molecules to pass through while blocking salts and impurities, resulting in fresh water on one side and a concentrated brine solution on the other. Another method used in desalination is distillation. Distillation involves heating salt water to create steam, which is then condensed and collected as fresh water. This process separates the water from the salts and contaminants, producing pure drinking water. But why does it take such complex methods like reverse osmosis and distillation to make salt water drinkable? To understand this, we have to examine the process of when an ionic compound, such as salt, dissolves in water. When an ionic compound is added to water, it dissolves and dissociates, meaning that the compound's ions separate and become surrounded by water molecules. The positive ions are attracted due to the negatively charged ends of water molecules, while the negative ions are attracted to the positively charged ends of water molecules. Because, like dissolves like salt is soluble in water, substances that have similar intermolecular forces or polarities tend to be miscible, meaning they can mix and dissolve into each other. Salt and water are polar compounds, meaning that they can mix together. On the other hand, substances with contrasting intermolecular forces or polarities may be immiscible and form separate layers. Since water and salt mix so well, it makes it very difficult and expensive to separate the two. This is the reason why desalination requires such advanced technology and a lot of energy and resources. Water and salt being miscible isn't the only reason why desalination is difficult. Different areas around the world have different concentrations of salt in their water, which might affect the desalination process. For example, the Red Sea and the Persian Gulf have a very high concentration of salt compared to the Atlantic or Pacific Oceans. In chemistry, we distinguish between concentrated and diluted solutions. A concentrated solution contains a large amount of solute dissolved in a given volume of solvent, like the Red Sea and Persian Gulf, and a diluted solution has a smaller amount of solute dissolved in a larger volume of solvent, like the Atlantic or Pacific Ocean. Higher concentrations of salt in water can pose challenges in desalination. It may require additional energy, more extensive pretreatment, and advanced separation techniques to achieve the desired freshwater output. Conversely, lower salt concentrations in the water facilitate a more efficient desalination process requiring less energy and resources. Because different areas have different concentrations of salt in their water, the price of desalination may differ, meaning that areas with higher concentration of salt will have a harder time with desalination. Unfortunately, most places that need fresh water are unable to afford desalination. But advancements in desalination technologies are making the process more efficient and sustainable. Innovations in energy recovery system, membrane technologies, and renewable energy integrations are helping to mitigate the environmental impact and reduce operational costs. It's crucial to strike a balance between the benefits and drawbacks of desalination. While it provides an invaluable source of fresh water in arid regions or areas with limited access to traditional water sources, it's essential to consider the long term sustainability and environmental implications of large scale desalination projects. Research and development efforts continue to explore alternative desalination methods such as forward osmosis and nanotechnology, which hold promise for more cost effective and environmentally friendly solutions.